Hi, and welcome everyone to this session on machine learning, an introductory session on machine learning. So I'm Tess. I'm a developer at Microsoft. I'm going to do this in English because I know that there are some people in the crowd that don't speak Swedish. I hope you don't mind. So I'm a developer, and I've spent most of my career analyzing memory dumps, finding patterns and anomalies in big chunks of data. And it turns out that that's kind of exactly what machine learning is. So when I later started focusing on machine learning, it turned out to be a very, very good match. So what we're going to do today is we're going to go through essentially like the different parts of machine learning to make them less scary and to make sure that either you have a good basis for continuing a journey to machine learning, or maybe just to see if you have some projects that would fit in and kind of figure out if what you think are machine learning projects or not. So I'm going to start with one example. I have two pictures, obviously. One of them is of a muffin, and one is a chihuahua. I'm not going to say which one is which. Who of you thinks that this is a chihuahua? Okay, pretty good crowd. Okay. So how did you know that? I'm going to start with you in the first row. It's hairy. Okay. So any other? Eyes? Maybe an eyes, nose. Essentially, you probably know that this is a chihuahua, A, because I said one of the pictures was a chihuahua, and you either saw enough chihuahuas to know that it is a chihuahua, or, like me, you didn't see enough muffins to know that at least it's not a muffin, and so it has to be a chihuahua. So if we were to do this is a problem called classification, like classifying a picture as either a chihuahua or a muffin. If we were to do this using traditional development techniques, it would look something like this, right? Eyes, nose, whatever. Apart from the obvious fact that picture contains is kind of a hard piece of code to write, and that I can't spell chihuahua, which I noticed this morning, there is another problem with this. And the other problem is that when you're faced with something like this, it really doesn't work, right? So how do we solve this problem if we can't use traditional like if-else statements? Well, one way to do this is through machine learning. And machine learning in this case, what we would do is we would throw enough pictures of chihuahuas, saying these are chihuahuas, at a machine or at a computer. The term machine in this case is because machine learning is like 60 years old or 50 years old, and back then it was more machines than computers. So we would throw enough pictures of chihuahuas, labeled chihuahuas, and enough pictures of muffins, and then have the computer kind of figure out what's the pattern that makes this a chihuahua and this a muffin. So this is a problem that's pretty common in machine learning, and it's also a problem that is already solved. It's solved in many ways. One of the ways that is solved is in Microsoft Cognitive Services. So if this is a problem that you're trying to solve, you don't actually have to know machine learning at all. You can just go up to Microsoft Cognitive Services and throw a picture at it and say, and it will return, like with a JSON file, saying it's a dog, it's indoors, it's cute, it's black, or it's white and brown, and a bunch of other information. And you don't have to know anything at all. So again, Microsoft Cognitive Services. That's not the type of problem we're going to talk about. We're going to talk about some other issues that are not already solved. But if we look at some of the more common machine learning issues, like for example, face detection, that is also a problem that is solved, something that you can just call an API and it will figure out like where your face is, who your face is of, and all that stuff. Sentiment analysis. Let's say you're a big company, you've just released a new phone. It has, like, you think it's top notch, and now you want to figure out if everyone else thinks it is. So you can throw the Twitter stream about your product, like anyone who mentions your product, through sentiment analysis. They're doing Samba in the next room, if anyone wants to join them, okay? So you can throw that Twitter stream through sentiment analysis and figure out if this person thought it was good or bad, or you can throw faces at it, like pictures, and it will tell you if it's happy or sad or surprised and things like that. Now, there are some issues that aren't solved because they use very specific data. Like, for example, if you want to know what the stock price is going to be next week, you can do machine learning on that, but that's a typical problem that we'll talk about today. Or if you want to know if, for example, a credit card statement or a credit card transaction is fraudulent, or if you're Netflix and want to kind of recommend certain movies to certain people. So apart from liking machine learning and analysis, I also like houses. How many of you have been to Hemnet last week? Quite a few? Okay, so I've had the same house for 10 years, but I've kind of gotten addicted to going to house showings. So at one point, actually last summer, I think I went to 6 showings just in one weekend before an intervention by my husband, and now I try to limit it to 1 or 2 a month. But what I've decided then is to kind of be able to keep this up. I've turned it into science. So I'm doing machine learning on my showings. So what I do is I've recorded a lot of data about these houses. And by the way, what we're going to do now is we're going to take the machine learning process and do it the manual way, so you see like how all the steps are done. So what I've done, and this is actually for real, I'm not kidding that I've done this, and I have long lists of bidding wars and stuff like that to analyze how that's happening. So I have a list here of square meters in houses and the price in 1,000 crowns. So for example, a 134 square meter house was 5.5 million. And now we're going to do some analysis on this because we're going to try to find out how much a 150 square meter house is worth. So the first thing we do after collecting the data is to try to analyze it and find out like relationships between features. Features are like the input values, like the area in this case, or does it have a pool, or what's the quality of the house, location, all that stuff. And then we plot it, so you can see here 134 was 5.5 million. And we plot all the data, and then we end up with something called a scatter plot. So this is just one of the diagrams that you can use for statistics or for machine learning. And you can do this in Excel or whatever tool you want. But this is a very common plot to figure out a relationship between 2 numeric values, like the area and the price. And now, here comes the machine learning. By the way, I noticed that I wrote down 40 million for a 98 square meter house. Yeah, I didn't at all prepare this to be machine learning. So I need to clean the data also to make sure I don't have any errors in it. Then when I plotted it, now it's time to figure out how much the 150 square meter house is worth. So I'll take you. How much do you think the 150 square meter house could be worth? 6? Yeah, somewhere around that. So how do we figure that out? Well, one way is, we can kind of gauge it with our eyes, but the real sciencey way is by creating a model. In this case, a straight line, because we kind of see that the points kind of look like a straight line. So we can approximate like the point to a straight line. And this straight line is called linear regression. And this is one of the algorithms that we use in machine learning. It's not super common because it's kind of rudimentary, but it's the basis for many other machine learning algorithms. So we choose an algorithm that we think fits our data pretty good, linear regression, and then we fit it. So we look at the points and try to make sure that the line kind of goes in the same direction as the points. And that is called training the model to the data. And then now we suddenly have something that we can actually use for prediction, right? We can now actually figure out that a 150 square meter house should be 6.2-ish, so you're pretty straight on. But notice I said the word prediction, because that's all that machine learning is. We cannot say for sure that this is the correct value, but we're going to guess that this is a correct value. And when you guess, you might also be wondering, like, okay, so how good is my guess? And that's the next step of machine learning, to kind of figure out, like, validate how well your model is doing. And when it comes to linear regression, a good way to do that is by just using a highlighter and creating like an envelope around all the dots. And this will give us something called a confidence interval. So this is telling us that I'm going to guess that the 150 square meter house is 6.2, give or take 500,000-600,000 crowns, because that's like how well it fits in the confidence interval. So we've gone through the whole process. So we gathered the data, or actually first we asked a sharp question. I'm going to get to what a sharp question is, but we asked, how much is a 150 square meter house? And a sharp question in this case is something that can actually be answered with the data. Like, we have historical information of other houses with square meters and prices, and we can use that to predict this value. Then we gathered the data, we cleaned it, we explored it, and sometimes we can also do things like transform features. So for example, the square meter, we might want to change that into, like if we have the square meter plus the square meter of auxiliary areas, like B area, then we might want to put that together to a total area, so combine features and things like that. And then we select algorithms like the linear regression, like the line, to make sure it fits our data. We train it, so we put the line in the right place, and we use the answer. And using the answer is also, of course, extremely important and kind of forgotten in some ways. So now we're going to go through all of these in a little bit more detail, because there's a little bit more to machine learning than just this very simple sample, because here we had two values that we were comparing. They were pretty fair, like they were nicely aligned, because I just picked ones in a very small area of Sollentuna that were kind of similar, but in reality the spread is a lot wider. And so we're going to look at how you kind of refine it and make it better. So let's start with the question. It turns out that there are actually just 5 questions that you can ask machine learning. I don't know about you, but when you think about AI, you think about a little bit more than 5 questions, maybe. But there are 5 question types that you can ask. And the first one is regression. This is what we've been talking about before. This is how much or how many. So how much does this house cost? How much will, like, how good will the Google stock be on Thursday? Like, what price is it going to sell at? Or what's the temperature in Stockholm this afternoon? Or how many people are going to buy the iPhone X? That's the kind of stuff we can learn with regression. Then we have classification. We've already seen one example. Is it a Chihuahua or a muffin? But here you typically have things like, this email, is this spam or is it ham? Like, should it be sent to the spam box or to the inbox? This person who has these symptoms, will she develop diabetes or not? And this news article, like on a blog or whatever, if you want to tag cloud something, is this news article about .NET or Java or music or whatever? And so you see, it can both be 2 class and multiple classes that we can do classification on. And then we have a special kind of classification that's called anomaly detection. So anomaly detection asks the question, is this weird? Is this transaction fraudulent? is this log entry in my internet log weird? So should I be worried about it? And while it is a classification problem, kind of, it's very different from classification problems in that normally classification problems have very similar classes, as in like there are almost the same amount of this class as this class as this class. But in anomaly detection, you have everything is normal, and then you have like 0.0 blah 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 percent anomalous stuff. So you have to use totally different algorithms to figure out if something is anomalous or not. Then we go into unsupervised learning. So previously, like, we have data that says, here is the input, here is the output, now learn from new input, give it new output. So we know kind of what we're looking for. Now we get into unsupervised learning, where we don't actually know what we're looking for. So in this case, we have, for example, a set of products, and we want to group them in some way. We're not saying I want to group them as tablets or as laptops or whatever. We say group them in 5 groups of similar objects. So we can think of, for example, using this for movie recommendation, because you might want to group similar movies that similar people like. Or even like grouping people as these people seem to like the same things, because they're kind of like, we don't know what the specification for grouping them are, but they could be the same age or the same gender or whatever it might be. So this is called clustering, and we say how many groups we want, but we don't say anything about what we want the groups to be. And then finally, we have something called reinforcement learning. So reinforcement learning, if you think about it, is, for example, it's when you have a temperature system and you want to know if it's going to go up, like if it should move the temperature up or down, or if you have a vacuum cleaner and you want to know if it should keep vacuuming or go back and charge. So reinforcement learning, the way it works is a little bit like kids learn, in that, for example, if you touch a hot stove, then you get feedback saying, this is really bad, and you're not going to touch that anymore. Same way it works with reinforcement learning. Like, you do something, you get negative or positive feedback. If you get negative feedback, you continue doing it. And if you get positive feedback, you stop doing it. Okay, so now we know what questions we can ask. And the next step is then to collect the data. I'm just going to give a few examples of collecting data. So one that's very common is through sensors, for example. At our office in Kista, we have sensors that tell us like how often people sit at certain tables, how often they use the restrooms, that kind of stuff, to be able to tell how often they should be cleaned, or if we should move conference rooms together, so we can do analysis on that data. But then you can obviously also gather it from the internet. Like I've been gathering data from Hemnet, for example, from their end prices. And then if you just want to get started in machine learning, you can try out with sample data sets. So there is a site called UCI and a site called Kaggle. Kaggle is for competitions in machine learning, but they have a lot of good data sets for you to kind of practice your skills on. Like the Titanic data sets to predict how many people survived the Titanic, or wine data sets to predict the quality of the wines, or even a data sets on like 800 UFO sightings, if you just want to predict if a UFO is going to hit you right here. And independently of how you gather the data, you're going to put them in a table. And you're going to put them in a table that kind of looks like an Excel spreadsheet. So even if you have data in multiple tables, you have to kind of gather them in one. And every single one, now we're talking about supervised learning, we have something called a target. And the target is what we're trying to predict. So in this case, the house price. And then you have the other columns, which are sort of the input variables to the algorithm that we're going to use to predict them. And they're called features. And each one of these rows is something called an observation or an item, or just, in this case, one house sale is one instance. And the values that you can have can either be a number, or getting kind of basic, but it's also a little bit important for the algorithms. So it can either be a number, like the area, or it can be a category, like the house type. Is it a villa or a townhome? And finally, it can be something, for example, it can be something like a zip code that kind of looks like a number, but it's not a number. And why is that important? It's important because when you look at the algorithms, what they will do with numbers is they will add them or subtract them or multiply them or do things to them. But you don't want to do that to something like a zip code, for example. So you need to make sure to mark them as a category. So when you look at features and what features you should use as input, there are a couple of things that you can think of. The first one being, is it relevant? Is this actually something that's going to help me predict the house price? Like the area, for example. Or the distance to water, because that seems to be something that really increases the price. So that would be a good feature. On the other hand, like the number of chickens in Alabama at the time of the house sale, maybe not so relevant. And then you might have things like the broker, that they really kind of upplay their relevance, but I've done some research on this whole data set, and it turns out that actually the broker was kind of insignificant in terms of like how high the value was for the price. Don't tell anyone. But the other one, so relevant, the other one is that they have to be independent. So by independent, I mean, like if you have the area of the house in square meters, you don't also want to feed it the area of the house in square centimeters, because that will kind of add the same data twice and upplay the importance of that data. Now, it's pretty obvious when you talk about it like in meters and in square centimeters, but if you talk about things, for example, like the area in square meters, and then you add the number of rooms, which is highly correlated, like, I mean, the number of rooms kind of like sort of depends on the area, you might just want to pick one or the other to not kind of upplay the area piece. And finally, they have to be simple. And by simple, I mean, in this case, if we have the GPS coordinates for the house, that is not super useful to a machine learning algorithm, because if you're comparing like one GPS coordinate to another, it's very hard to say if one is better than another or not, or if one should add to the value or subtract from the value. If, on the other hand, you convert this to distance from water, like so you have some point where you can say, okay, so instead of the GPS coordinates, it's like 10 meters from the lake, or it's 100 meters from a school. That is very important information, and that's something that you can actually use to determine like the trajectory of the price. So relevant, important, and simple. So now that we have our features, the next step is to explore the data. And this is something that you can do, for example, in Excel. Like it works super well to do data exploration in Excel, at least basic data exploration. You can easily create like these scatter plots. You can even add like the linear regression lines if you want to, and figure out like how well they correlate. The other two that I'm showing here is one that's very popular for machine learning. This is Python, and specifically it's a Jupyter notebooks. So when you install Python, something that's cool. First off, if you've never used Python, Python is a very, very simple language, and if you know C# or if you know something else, then you're definitely going to learn Python extremely fast. What's cool about Python is that it's a language that you can use interactively in a web browser. So in a Jupyter notebook, what you do is you write a piece of code, and then you write Markdown, and you can kind of continue writing your story and doing a little piece of code to display some values or display some diagrams, and then talk about what you saw, and then do another diagram. I'll show you a little bit about how that works in a bit. And then finally, this is Azure ML, Azure Machine Learning Studio. So it's one of the Microsoft machine learning tools that you can use. So if you have an Azure subscription, or even if you don't, you can kind of create a free Azure machine learning project. And you only pay for it if you've used up a certain number of hours and things. And in Azure ML, first off, it lets you do the proper machine learning, but it also lets you kind of go through and look at your data. And then at Ignite, we also announced a machine learning workbench. I don't have a picture of that, but that's something that you can download and try. It's not really in production yet. So independently of what you do, when you explore data, you want to look for a few things. You want to kind of look through your variables and see how they correlate and how much cleaning and stuff you need to do, because in the next step, we're going to take what we learn in the exploration and kind of clean up the data set and prepare it for machine learning. So you go through, and first you say, is the variable a category or numeric or things like that, so that you can properly mark it for the machine learning. And then you go in and you kind of do a mental note of what do you think, what kind of expectations you have of the data. Is it high or low probability that this will actually have an effect on the target? And and then you have to go through and look for badness in the data. Specifically, if you have data that's missing, so something that wasn't filled in. In my case, I have a lot of the early prices didn't have like addresses and things like that, so you might need to do something about that. Or something called outliers, and outliers is when you have very odd values, like something that's very out of the norm, very out of the ordinary. So what specifically you're looking for is duplicate items. So for example, if you were to pick house prices from Booli, they have a recording both of when the house is sold and when the house is transferred. So each sale is kind of marked twice, and you kind of want to avoid that, so you need to remove those kind of things, because otherwise you'll get weird and skewed data. And then you want to remove irrelevant observations. So let's say you're creating a model of detached homes, villa. You might just want to remove the townhomes, because they might have a totally different, like when you're looking at, for example, an apartment, you're looking for totally different things than when you're looking at a detached house in terms of like locations and stuff like that. And then, as I said, outliers, missing data, and structural errors. So structural errors means, for example, in this case, when we have the region of the house, brokers like to type them in very, very differently. So you might have things like Östermalm, and then you might have things like Stureplan, but they're really the same thing. Or someone might write down Östermalm/Stureplan. So you have to kind of figure out how they belong together. And when you look at the data itself and look at outliers, for example, here we have an example of, this is the actual area compared to price. And in this case, we have one dot over here. That means that we have a 500 square meter house, whereas all the other homes are around like less than 200. So that means that we probably should take care and remove that particular one, because if that skews the data, it's going to make all the other prices wrong, so to speak. So you want to take away like things that don't seem to follow like that line. And I'm just showing you, these are just like some examples of plots that you can see when you do exploration. So the other one here is a correlation plot that will tell us how much the values depend on each other. So we have, for example, the area, and if we compare that to rooms, we can see that it's like 0.81 up here. that means that it's very highly correlated. The higher the area, the higher the number of rooms. So if it's that correlated, you might want to remove one of them, for example. Okay, so now we have that, and we start deciding on what we're going to do with missing values and things like that. So in here I have one example, like in the area, we decide to remove the area, like remove any rows that don't have area, because area is so significant for the price that any observations that don't have any area are kind of like useless anyways. And in some other cases, like for example, when we look at the supplemental area, B area, if that's missing, let's replace that with a 0 instead, because that's a normal thing to be missing in this data. So you just go through and figure out what to do. And here I've listed, like, as far as outliers, when the area is above 500 square meters, let's remove that row altogether. So once we know what to do, we then go through and clean the data. So this is an example of a very important data set of superheroes and whether or not they wear capes. Obviously a big research area in machine learning. And we're going to go through and look at how you go through cleaning the data. So first off, the ID and first name and last name, we're going to remove those altogether from any type of machine learning, because we can't trend on a name, like they're all unique, for example. So we're going to remove them eventually. But the birth year, you see, it's been entered in all different sorts of formats, so we have to standardize it somehow so we can kind of fit it into a mathematical algorithm. So what we do is we take this and clean it up and make it really nice. And you see one of them, for example, was a minus because it was before Christ. So in that case, it's okay. We just replace that with a minus. Next one, the height. We have kind of uniform data. It looks pretty good, but it has one big issue. It's American, which we all know how that goes. Well, the problem with that is that they use this weird format of feet and inches, which you can't really compare all that well. Because you can't take them minus each other, and like it doesn't follow the decimal system. So a good thing that we could do would be to just turn it into inches instead, because this is now something that we can subtract or add. The next one is a categorical one with the birthplace. It's okay to leave it as is. And the next one, identity, secret, we have a bunch, first, structural errors. Like we have something called missing, that should probably be not. And we have missing data that we need to fill somehow. So now it's time to go back to like the domain expert or whoever gathered the data and figure out how should we deal with these. And the correct way in this case was to change all the missing to not secret, and yes and y, let them be y. We'll do the same thing with can fly, alignment, and wears cape. So this is kind of a tedious process that you go through, but and probably one of the kind of longer phases in machine learning to go through and clean data like this, but it's also a very important one, obviously, because otherwise it wouldn't work well in machine learning algorithms. So we're now halfway there. In fact, I would say like the whole cleaning piece is probably going to be like 80% or something, like the exploration and the cleaning piece. Sometimes you wouldn't even like go through and do any machine learning after this, because you've learned so much about the data in the exploration phase that you can just answer the questions without like a prediction algorithm. But if we get here, we might want to transform features. So transforming features means that we take that GPS coordinate and turn it into distance from water to something that the machine learning algorithm can actually use. Or if you're doing ice cream sales, instead of having a date that you're looking at, you might just want to turn it into summer or winter, because that's going to be super relevant for your algorithm. A typical one, for example, is if you're doing, like there's a bike rental data set, that's one of the training data sets. So one of the things you do there with transforming the features is figuring out if the date is on a holiday or if the date is on a working day, because that makes a big difference for the bike rentals. So just figure out like how you can use the values that you have and turn them into something useful for predicting the values. And how do you do this? Probably the best way is looking at, if you were to do this manually, if you were to predict based on this data what the value should be, how would you do that? How would you figure out like what the price of the house should be? And how would you, kind of from the GPS coordinate, how would you figure out if this was a good or bad house? And then we get to the actual machine learning part, because up till now we haven't done sort of any machine learning. And this is selecting the algorithms. I'm going to go through a couple of algorithms, like actually a couple of the base algorithms, and then essentially most machine learning algorithms kind of build on top of these base algorithms. So the first one we've already gone through, linear regression. Typically, like, so you would think, for example, if you were to find out the price of the house, then we could just do it in Excel and let it be over with. But the problem is a little bit that you wouldn't normally have just one feature. You want to refine it and have, you know, all the other information about a house, and suddenly it's not so easy to plot the data in a two-dimensional graph. But still, linear regression can kind of, like, you enter all the values and you can get like still a linear regression line or plane or a hyperplane. But linear regression is also kind of the basis of other like lasso regression or other refined algorithms that take care of selecting the features for you. The next one we're going to look at is something called a decision tree. So decision tree is sort of like if-else statements. That's what it's going to turn out into in the end. So we're looking at, this is also like a classic training data set, where you figure out, like, during certain conditions, people are going to play tennis or not play tennis. And you might use this as the basis of finding out how many people should you have in the tennis store, for example. So the way decision trees work is a little bit like 20 questions. So I'm thinking about a person. What would be the first question that you would ask? Like, let's say you. If I'm thinking, like, have you ever played 20 questions? Yeah. So is it a man or a woman? That is probably the first and the best question, because that kind of divides the population into two different parts. And that is what decision trees do. Like, they try to divide your population into as big, like as clean groups as possible. So we go back to this data, and I want to say, okay, so what could we use in this data to clearly separate the yeses from the nos? I've highlighted the yes so you can kind of see which ones they are. So I'm not expecting you to actually do this, but one thing we could use is say, is it overcast? So is it cloudy? Because if it is cloudy, it turns out that every time it's cloudy, people will play, right? So we can use that as the first one and say, if it's cloudy, then we will play. And then we'll look at the rest and say, okay, so now how do we divide the yeses and the nos? Well, if the humidity is high and it's sunny, then people will not play. But if it is, then they will play. And then we can go through and do windy, yes or no. If it's rainy, that will also divide us up to decide if we're playing or not. And this is how decision trees work. So eventually, in the end, you'll get a classification. Obviously, this will, well, you'll have to have much more questions normally for a long data set, and it's also not that clear cut. So what you would normally do in a case like this is you would create a lot of decision trees based on small sets of data, either a number of instances or a number of features, and then combine them together and average the results out. That's called bagging or boosting, depending on how you combine the trees. But that is the basis for a decision tree. And then we have something called naive Bayes that works on probabilities. So in this case, we have a number of emails that are either ham or spam. We separate them out into some that are spam, like these are all the emails that I got today, for example. And we'll say, okay, so how many of these have spelling mistakes? And it turns out that all my spam emails have spelling mistakes, and some of my regular emails have spelling mistakes. So we remove all the rest, and then we say, if it's got a spelling mistake, what is the probability of this actually being a spam email? You? Putting you on the spot for math. Is it 40, 75, or 90? 75, actually. Like, sorry, I didn't mean to put you on the spot for math early. So, if it got a spelling mistake, then it's got a 75% chance that it's spam. And then you go through other things like, does it contain the word sheep? Does it not have a title? Is it from certain countries? Or does it tell you that you're going to win $40 million? That kind of stuff. And then you combine these together and you figure out a probability that this is spam or not spam. And that is called naive Bayes. Now, the next one is for categorizing apples and oranges. So in this case, we have all the green dots are apples, and all the orange dots are oranges. I'm going to pick you in the green. How would you separate the apples from the oranges? Yeah, so this way, maybe? Yeah? So you like writing a line. So this kind of looks a little bit like linear regression, except for it's not. It's called logistic regression when it doesn't really actually look like this, but you can think of it separating lines like that. Or a support vector machine is also one of the ones that kind of divide with a straight line like this. Now, you've probably all heard of neural networks. So neural networks is when it's a little bit more complicated than just a straight line, and a straight line or a straight plane won't really do anything to it, then you might want to use multiple lines. You might want to combine two algorithms or two logistic regressions, like two lines like that. And then you say, in the first case, you put in this case, acidity and sweetness, and you say, okay, so if it fits on top of this line or below this line, we have different categories. And then the same if it fits on top of this line or if it's below this line. So then you combine them. So if it's an orange in this case and an orange in this case, and we add them together, then it's an orange in the next step too. And so neural networks is sort of like a way to apply multiple layers on data, combine them together, and create more, more complex algorithms. So this is kind of cool because the way you do this is you combine so many together, but you don't exactly know, like you don't have to decide on beforehand what it's supposed to be looking for. So you combine them together, and eventually you'll end up with a network that doesn't necessarily, like, you don't have to tell it in advance what features it should look for. So this is something that's kind of useful for an image where the features are actually each and every single dot, like each and every pixel of the image. And you don't want to kind of do all the feature transformation and all that stuff. So which algorithms should you use when you do machine learning? Well, it's kind of tough to know in advance, but there are cheat sheets like this. So this is the asscher machine learning cheat sheets. There are plenty of them, like scikit-learn, which is a Python module. They have cheat sheets for this to know which ones to use. But essentially what you'll end up doing anyways is you'll end up testing it with a bunch of different algorithms that fit your problem. So if it's a classification problem, you might end up like spot testing with a number of different algorithms to see which one seems to look best, and then you refine that particular algorithm by changing the parameters. Now that we have all the data and we've looked at all the algorithms and we've chosen a couple of algorithms, it's time to train the model. And training the model, the process looks a little bit like this. And I've actually written it like this because this is very similar to how it looks in Azure Machine Learning Studio. So you bring in the data, you clean it, and you might even clean it on beforehand. So I would typically clean it in Jupyter notebooks or something like that on beforehand, and just add in clean data. And then you split it up into training and testing. And the reason for this is because if you train on your data, you will never know how the algorithm will work on unseen data. So if you train it on the data, it will kind of conform to that data that you train it on. But you now want to have some clean data that you can verify your algorithm on and kind of figure out how well it actually did. And then you select an algorithm, you train the model, you score it. Scoring means that you're actually going to use that model to say, this is an apple, this is an orange, this is an orange, this is an apple, that kind of stuff. And then in the end, you evaluate and calculate how many did it get right and that kind of stuff. So we'll look at how that looks in Machine Learning Studio. By the way, this is Jupyter Notebooks. And this is how you do the exploration. So you just write Python code, run it, and it will show plots like this. In fact, this is real data from Hemnet, and here we have a sort of an interesting scenario where the average square meter price for houses, like for detached houses, suddenly dipped and went below the average square meter price for townhomes, which was kind of odd. Do you guys know what happened here in 2016? No? Am I the only one interested in houses? Yeah. Yeah. So we had that big law that made you have to pay off your loans faster, right? So that had a good effect on the prices for like half a year, and then it went up again. So yeah, interesting. So to do machine learning then, this is Azure ML Studio. So I've saved a data set with the houses. And now we can go in and drag and drop things. So the first thing we're going to do is we're going to just select which features we're going to be using. So let's do select columns. I'm going to pick out a few other ones here. And I'll kind of talk about them once I have them out here. Train the model. We're actually going to do 2. And score. And then finally evaluate. see. Okay, and now we also have to pick a few models. But let's start with this. So we're going to select the columns that we want in the data set. So we're going to launch this column selector. And I'm just going to choose the ones that I know I want. So here we have, for example, the area and the supplemental area. I'm going to just pick both of them. I could have used, like, for example, the total area instead, not the rooms, maybe the land area, the monthly fee if it's a lease house, and then running month is like the month starting from January 2012, because that's when I have data from, and whether or not it's a townhome or it's a condo. When you open it up like that, you can then go in and visualize the data set from the beginning. So here we can see like histograms, so we can kind of follow the prices or the areas, if it's normalized or not. And we can do things like compare this to the price, and we'll end up with like these scatter plots, which is kind of like the exact same scatter plot we saw before. Once we've selected the data, we're going to go in and edit the metadata. And what we want to do here is specifically go in and pick out and say that some of them are categories or not. I'm actually going to go ahead and run so I have something to pick from. Okay. Actually, it will not run because I have too many errors in it. So I'm going to do is condo, and the house type, and the region. All of those were category values, and the rest of them were numeric. So I picked those, and I chose make categorical. And then I'm going to go in and split the data, and here you split into what you think, like what you want to train on and what you want to test on. Eventually, like you actually want to try to do things like a fold split, like a 10-fold split that will train first on everything but one piece, and then on everything but another piece, so you can use the whole data as your training data set. But for right now, we're going to split it out into 80% for our training and 20% for our testing. And we then use this as the input for our models. And then when we go in and score the model, instead we're going to score on the test data set, which is the right-hand side here. In that case, we're just going to send in the trained models. So it's a whole lot of drag and drop going out here. And then eventually we'll score both models and compare them to each other. So now it's time to select our algorithms. And in this case, we go into let's see, the machine learning piece, and we know that this is a regression problem, right? Because we're looking for a number. And so we pick from regression, and we can just pick a few of these. I'll just pick a linear regression and a decision forest. So it turns out like decision forest or decision trees can also be used to find out numbers, not only categories. We pull them into the training, and here it says we need to say something because we need to know what we're actually going to look for. We're going to look for the price, and same thing there. And at this point, we can actually go ahead and run this. And now it's going to go through and train the model and actually do the machine learning for us. So, depending on the amount of data you have, obviously this will take more or less time. Hopefully this should be fairly quick because I have only like 1,000 samplers or something. By the way, all of these, oh, something went wrong with this. Crap, I didn't pick I'm actually going to go ahead and pick one of my previous experiments instead of having you look for what I did. It's the exact same thing, except for here I've actually gone through and trained it. So for the different algorithms also, they have something called hyperparameters. So it could be things like in decision trees, you might want to put in how many levels you want of the decision tree, or in decision forests, how many different trees that you allow, that kind of stuff. And all of them have those, and you want to go through, and once you've picked out the models that you like, you want to go through and kind of refine and select select those parameters for them. Once you've trained the model, if we look at the decision tree and visualize that, we will then end up with a number of these decision trees that looked exactly like the ones that we looked at in the tennis data set, except for way, way bigger, right? Or if we visualize, so here it has like a question about land area. If it's higher than 751 square meters, then go one direction. If it's less, go the other direction, and so on. And same thing for like the linear regression. If you visualize it, what you'll find out is like the parameters for the different parts of the naive Bayes algorithm. And then once you've trained it and scored it, you can also visualize. And what it will do then is it will tell you what it thinks are the answers for the different parts. For example, here, it picked 8,200,000 something. The real price was 7,045,000, so it was a little bit off. Well, quite a bit off, actually. And you do the same thing in the other scoring. So eventually, once you have them scored, you can then go in and visualize and find out like acceptance metrics or how good they are. Like how far off they usually are. Like in this case, 703,000 was the mean absolute error, like so the average absolute error for it. Obviously, that was probably not a really, really good machine learning model that we created, because I didn't have a whole lot of features like the quality of the house, and I'm missing a few other things that would have made it a lot better. But if we would have had a lot more of those, the average errors would be a lot less. Okay, so let's go back here. So at least you've seen now how it actually looks in practice, like how you actually do the full machine learning. And the metrics for defining how good your model is, if it's a regression model, you'll have things like mean absolute error or mean like root squared absolute error for saying like how far off you were in the numeric measurements. If it's a categorical measurement, like if it's ham or spam, then you'll have something like this, and this is called a confusion matrix. So in this case, what we have is like for spam, if it was actually a spam, did we guess it was spam or did we guess it was not spam? In this case, we had, for example, 100 ones that we thought that were spam, that we sent to spam, but we had 170 ones that were spam, but we guessed they were not spam after doing the machine learning on them. So in that case, we have a few different metrics. Accuracy is how many of the total ones did we guess correctly? Like how many of the spam did we guess spam? How many of the ham did we guess as ham? So in that case, we had an 80% accuracy rating. And it might be tempting to go in and think that accuracy is always the best value for measuring like a machine learning algorithm classification. But let's say, for example, you have something that's going to measure, like something that's going to predict if you have cancer or not. Then it might actually be more important to send some like to send all the sick people to a doctor's appointment and some of the healthy people than to not, like to miss a few of the sick people. Same way with spam, on the other way around, it's more important to not send real emails to the spam inbox. It's nice if you send spam to spam, but it doesn't necessarily really matter if you send them all to spam. It's okay if you just filter out the brunt of them. So in that case, we have other measurements like precision. So precision in this case means of the ones that we sent to spam, how many of them were spam and how many of them were not spam, because that's a very important metric. Like if we keep sending ham to the spam box, then it's not good. And that's, in this case, 100 divided by 130. On the other hand, like in the cancer case, we want to look at how many of the sick people did we actually say should go to the doctor? How many of the spam emails did we send to the spam box? And that's called recall. And that, my friends, is essentially all there is to machine learning except for the details. Yes. But hopefully you learned enough to actually be able to now figure out if your project is a machine learning project, like if you have some questions that could be answered with machine learning, and kind of have like a pretty good grasp of what machine learning does and what you can do with it. So with that, thank you, and I'll be here for questions.